Bismillahirrahmanirrahim. I am Usman Javed, and this lecture is basically the continuation of our last lecture on virtual work method for trusses. I have explained the work method and applied it on truss elements, bar elements. Now, in this lecture, we will discuss the um, virtual work method and solve examples for beam and frame elements. And as it's a continuation of our lectures on determinant structure analysis, so let's start today's lecture. The content would be the virtual work method on beams and frames to calculate the deflection and uh, rotation in the beams and frame elements by virtual work method. So I want to recall the background of the virtual work method. In virtual work method, what we do is we do apply the virtual unit load and unit deformation onto the beam or onto the frame or any other element, and determine the response of a member with respect to corresponding to that applied loading. And we also apply the real loads upon the structure and calculate the response. Response might be in terms of internal forces, that is compression, tension, that may be shear, some moment, or some may be deflection. So we do we do calculate the response of structure from by applying the virtual load and real load, and then combine the effect of both virtual and real load into the formula of into the respective formula. For for bar elements, we have a different formula. We have a n multiplied by n into L over AE, which would be integrated till the whole length of different members, or summation we could submit for the different elements. And we have a formula for beams. We have a different formula for beams, which comes up which we have derived in a previous lecture, and which come up from the flexural formula. And we also have a similar formula for the frames. So let's start having an example. For example, we have a beam element with the with the uniformly distributed load. So we want to determine the vertical displacement at point C. By the action of this load, the beam tends to bend downward, and we are interested to find the deflection at point C. First, we will calculate the reactions by the application of a real load. First, what we do is apply the real load and determine the reactions based on the real loads, which is RA and RB. And we can take the section. Basically, I have explained in my previous lectures that at what instant you can take sections. So before you take the section, you must keep in mind that you have a different section properties and different loading properties. In this case, we have a constant section throughout the span, so we will consider the loading type. So in this particular example, we have a loading which is uniformly throughout this beam, so we will take only one section. If the loading type changes, you must have to take the section before and after the loading changes. So in this case, there is only one section that might we can take, which is x1. We will take the x1 as a section, and we'll draw the section over here. And as it is a beam element, we will take the internal forces at that section point. So section point contains the v1 and m1. So these forces are basically virtual forces, and it's their direction are assumed. We can change the direction of these virtual forces uh, and then calculate these values. If these values are with this negative sign, then it means that our assumed direction is wrong. We have to change our assumed direction. For example, we have a shear value which comes up as v1 equals negative something. Then we will see that our assumed direction, which is downward, is wrong. you must have to take it in upward direction. But by the rule but conventionally it would taken as a downward on right section of a beam, and the moment would be counterclockwise at right section. um, Conversely, it would be upward on right section of the beam and clockwise in right section. So what we do is to take the different sections. For example, in this case, if we draw the section x1 and x2, the these forces must be same. So what I was explaining, that if it is a right section of a beam, then shear would be downward as a positive. You can change it, you can develop your convention as well, and the counter clockwise moment as taken as positive. If we go toward the leftward of the section, the convention would be conversely or change opposite, which is clockwise moment and upward forces will be taken as positive. So we will apply the virtual load on the beam at the point C and try to find out the vertical displacement. For a vertical displacement, we have to apply the unit load at point C of one kilonewton or something compatible to the units. Then we will determine the reactions. We have two reactions over here. How can we calculate the reactions? As we have two unknowns, and in case of a beam there is only one equation. uh, there are the two equation, that is sigma f of y equals 0 and sigma moment equals 0. Then by computing these two equations you can get up ra and rb. It's simple. So for the application of a virtual load, we will take the section x1 and x2 from the rightward. Make sure that the values of the section would remain same at this direction and in this direction. So a value of x and x1 and x2 is varying between its total width. It must not exceed with the span. So you have a uh, delta 1 at for x1 and delta 2 for x2. So you have as I have explained earlier, that you have to take the section after the loading condition changes. So we have to take the section before and after the application of a virtual load. So before application of virtual load, we have a um, internal forces like m delta 1, v delta 1, and after the application of a virtual load, we have a moment as m delta 2 and v delta 2. So you have a universal equation comes up from the universal equation that we have developed in the previous lecture from the flexure formula and by principle of a virtual work method. So here comes the m delta, which is delta caused by some virtual moment or virtual load, and the moment due to real values, and it's a bending stiffness in flexure, and it's a limit up to the whole length of the member. So if we apply the real load, we would have a theta c over here and a reaction. Because we are interested in finding the slope, so we are interested to find the theta over here. So by the application of a applied load, we have a bending at point C, and we'll calculate the reaction due to application of real loads, and we'll take the section. You can see there is only one section over here because it's a distributed load over here, and the nature of a load do not changes, so it is adequate to take the one section. So you have internal forces of shear v1 and m1, and you can also take the section after the application of a c, after the c point. and then you will apply the virtual unit couple at point C or a moment, because as we are considering the slope, as we are calculating the slope of a slope or deflection or rotation at point C, so we are interested to apply the moment over here. uh, so the moment is applied, unit moment is virtual moment is applied, and a resisting couple is applied on the supports, so to calculate its reactions. So the direction is taken as in same direction, but the value must be in negative direction. So you have a x1 x2 x1 and x2 section over here. You will calculate all these values of a moment, and you have this formula. You will compute it and find the theta. So it's easy to calculate the unit deflection and unit rotation by using the virtual work method. So we'll be discussing some solved examples. So for example, it's a simply supported overhang beam. um, Overhang portion is basically a BC portion, and AB is simply supported. At the end of a free and at free end of the overhang portion, we have a P load applied, and in this example we want to determine the slope and displacement at point C, whereas the whereas the stiffness is taken a constant for this beam, yeah, which is EI. Now what we do is we will apply the real load and determine the sports reactions, and take the different sections, then find out the moment values by the application of real load, and then apply the some virtual load at point C and determine the moment values and deflection values, and then calculate the deflection and rotation respectively. So what we do is we want to find the displacement at point C. Then for the displacement, you must keep in mind for the displacement you will apply the unit load, not a unit rotation. For the slope calculation, you must have to apply the unit rotation. In this case, we will apply the unit load of value 1 at point C. So 1 kilonewton is applied, and then we'll determine the support reactions. So you have a two unknowns, which is AY and EAB, and you have two equations of equilibrium, which is sigma f of y equals 0 and sigma moment at any point equals 0. You will calculate the reactions of this beam by computing your values by solving these two equations. So you have a 1 over 2 and 3 by 2 value, so it is easy to calculate it. Contrarily, you can also calculate it by reactions by converting this unit moment into this unit load into a moment value, which might be 1a, 1 multiplied by this overhang portion, and 1a would be applied at B in clockwise direction. For example, 1a is your answer for the moment resolution. Then you will apply the resisting couple upon the beam, which is basically 1a divided by 2a, which forms the 1 over 2 and 3 over 2 values respectively. So it is easy to find your reactions by any means. You can solve the sigma f of y equals 0, sigma f of moment equals 0, or transform this value into some moment value and then take your values. So after the calculation of reactions, you will draw the moment diagram, as we are interested in the deflection. So for the moment diagram, you can draw the shear diagram as well to calculate the moment diagram easily, or cross check your moment diagram. But in this case, we will also draw the moment diagram, which is minus a over here and then goes up to 0 at free end. So the value of moment at this support is negative a. So it means that this unit load is basically hogging this B support, or this element over near the B support. So we will determine the values, we will compute the values of moment, uh, which is x1 over 2, if we take the section over here, and we will also take the section after the B support, or you can take section from C as well. There are two sections, x1 and x2 section. You will take the section and determine the moment value. We can easily calculate it, like if we draw the section over here. So if we draw the section x1, so what we do is we will calculate the moment m at x, which can easily be calculated as 1 by 2 times x. So moment value would be equals as 1 by 2 times x. How can you calculate it? Like you have a you might have to take the moment over here, and your assumed direction of a moment is this first, which is clockwise, and the moment due to this reaction is also a counterclockwise, and then half reaction 1 over 2 multiplied by x distance minus, and this moment m. So this moment would equals to minus 1 by 2 over x. Similarly, we can calculate the calculate the moment at this section by multiplying 1 into x. So the moment would be in this direction, so it would taken as negative. So this is moment at section 2 and this is moment at section 1. You can calculate it. These are the values of moment. So the m theta 1 would be minus x1 over 2, and m delta 2 would be minus x2. You can see that there is a rotation over here and deflection over here, because of the support. At hinge support there is only a rotation allowed. On the other hand, there is a overhanging portion which is free, and we can expect the deflection over here, as we are interested in the deflection, unit deflection. So in case of a real loading applied, the P will determine the reactions similarly that we have determined in previously for the unit load. We'll compute these reactions to form a moment diagram, which is minus PA at point B. So we will take the two sections and determine the moment values similarly that we have performed and done previously for virtual load at these two sections. So it is negative p x1 by 2, which is p by 2 multiplied by x1. So direction is counterclockwise, and the counterclockwise moment is taken as negative. Or you can supposedly use the different convention as you like, but make sure that this convention must be similar throughout your calculation. So for the moment m2, it would be p into x2. It is in clockwise direction, but it is rightward of your moment section, so it is taken as negative. So the convention you define changes from left to rightward. So here is the moment equation that we previously have developed, and we'll compute it the over moment values over here, and apply the limit. The moment values are at point at different sections is at this section for a visual load, which is a small moment delta 1, which is minus x1 over 2, and at this span you have a real moment of a negative px1 over 2, and you will sum this value with the overhanging portion. moment of overhang portion. For the overhang portion, you have a minus x1 for virtual moment and real moment as minus p x2. You will compute it. You will apply the limits are basically from 0 to 2a and 0 to a. You will integrate it with respect to x is a horizontal, um, x is basically a horizontal distance. You will apply the limits, which is 0 to 2a and 0 to a, and you will calculate the deflection at point C. The deflection is the function of a load and x distance, or a span. So in this way we can calculate the deflection in the beam by means of unit moment. For the rotation in the beam at point C, you would have to apply the unit load, a unit moment at point C, and then calculate all the unknowns, all the moment, small moment and capital moment, and compute it in the equation, and you will have a result of your rotation at point C. So here we go. There is a reaction of a 2a and 1 over 2a and 1 over 2a in opposite direction. You will draw the moment diagram. How comes the moment diagram is, you will if you cross check your moment values, you must have to draw the shear force and then add your moment diagram, or simply you can take the section over here and at point B and see what the moment value is. For example, I take the section at B and multiply this reaction, which is causing the moment at point B, which is 1 over 2a multiplied by 2a, which comes out as 1. So it is in counterclockwise direction, so it is taken as negative. Okay, so for the right, it goes with the zero slope till the free span, and it would make it to the zero level. So you have a moment value at over here. You will draw the section, multiply this value into the x. You will have a minus x1 over 2a, and over here you have a moment value of minus 1 because of this moment applied. You already have a moment values due to the real applied load. You will compute these values. You can calculate it simply by computing and applying the limits, and here comes the solution. So it's a rotation delta C at point C. Here simply in this way you can simply calculate the rotation and the deflection of a beam in a simple manner. So I'm leaving this example for you people to solve it by your own. You have stiffness values. You have to calculate the deflection and slope at point B using the virtual work method, and the virtual work method, using the similar approach, you will find out the rotation and deflection at point C. I am leaving this example for you to solve it at your own time and your own time. Now we will switch toward the frames, virtual loads of the frames. So we have a frame over here. It's a determinate. You can calculate the determinacy or indeterminacy by using the RA minus 3. It has a 2 reaction over here and 1 here. RA minus 3, it is a structurally determinate frame. So it has the properties of its flexure stiffness EI is taken as this, and you have to determine the slope and the horizontal displacement at point C, horizontal displacement at point C on a frame. Draw the bending moment diagram of a deflection curve. In first portion you have a slope and horizontal displacement at point C by calculating the virtual work method. So you will apply the virtual load of a virtual load of a 1 kilonewton at point C in this direction, and then calculate the deflection, and then you will apply the rotation of a 1 kilonewton meter and then calculate the rotation at point C. So here we go. You will solve it like you have previously performed. So you will apply the real load, which is 4 kilonewton, and calculate its support reaction first. So the support reactions are basically comes out as 12 kilonewtons. How can you calculate the force reactions? You can take the moment, sigma moment at point a equals 0, and you can calculate sigma f of x equals 0. Then you will come up with these values of moment, these values of reactions. It is simply to take that. For example, you have a 4 kilonewton force over here going in clockwise direction, uh, and you have a 2 kilonewton meter force which is UDL, in the form of UDL, which is applied at this span. So you will calculate the moment due to these forces. So here comes, so the clockwise direct, so these applied real applied forces would cause a clockwise moment, so the resistive moment must be anti-clockwise. So as it's a frame which is supported hinge and the roller supported, so we must have to form the couple instead of a moment, because the moment is not resisting either of the support. So you will form the couple of a counterclockwise direction. So couple would be in counterclockwise direction. You will calculate the effect of these forces, which is 4 times 6 24 plus 2 times 6 24 multiplied by 3, 2 into 6 12 plus 4 16 kilonewton force is applying in the leftward direction. So you will take this section at point x over here and over here. You will calculate the moment values by taking the moment m1. uh, for calculating this moment, you have to go to the into the frame and face the span AB, and A is your left side and B is your right side. Then you will calculate the moment value at this point, which is due to the application of a 16 multiplied by x1 minus this force, which is basically the 2 into x by 2, 2 into x by 2, which comes out as x1 square. So you have a moment value, you can calculate it you have a moment due to 16 multiplied by x, 16 multiplied by x1 minus moment due to this UDL. UDL is basically 2 times x, and it is applying on the centroid, which is x by 2, x by 2. So you can take as 16x1 and minus x square, x1 square, sorry. So it's simple to calculate the m1. Similarly, m2, which is due to the only reaction, which is 12 kilonewtons times x2. You will apply the visual load at point C in this horizontal direction of 1 kilonewton and find out the reactions due to this force, which is 1.2 kilonewton and 1 kilonewton. You have a two unknown reactions, and you have a two equations as well, which is sigma f of x equals 0, sigma moment at any point equals 0. You will compute and solve these equations to come up with reactions. So you will take the section from A and compute the value of moment, which is x1, and section over here, which is x2, and compute the moment, which is 1.2 times x2. So m1 and m2, we would be computing these virtual moments and real moments into the equation. These are the values of moments. This is small m1, and this is capital M1. This is small m2, and this is capital M2. So we can integrate upon the length. So the length is 0 to 6, and you have a length of 0 to 5. If we take the section from here, assume you can imagine, then you can take the section from B to C, then you have different limits. You will have to compute the limits of 6 to 5. So you can solve it as well. So the values of the integrated part would be as you know you have separate the stiffnesses, and you will integrate your variable, which is your length, and apply the limit 0 to 6 and 0 to 5, and you have these values, and you have a deflection of around 28.8 millimeters at point C. So in this way you can also calculate the rotation at point C by applying the unit moment. You will apply the unit moment, you will find the reactions by coupling the counter moment. The reactions are 1 by 5 and 1 by 5, and you will calculate the m1 and m2 for this. M1 equals 0 because there is no perpendicular force applied, and in this case half of x is m2. 1 minus half of x is x per 2 over 5 is your m2 because of this applied moment and this vertical force. Um you already have the real moments. You will apply this moment into the equation and integrate with respect to x, and the solution would be like, you have a 0.00125 radians of rotation, which is in clockwise direction, counterclockwise direction, which is in counterclockwise direction. As or as our unit moment is in counterclockwise direction, it is positive, it means that it is in counterclockwise direction. So in this way you can find out your value of moment and value of deflection and rotation for beams and frames. Thank you so much for watching this video. Hope you have learned a lot from this video. In case of any questions, you can ask in comment section, or you can contact me on your email, on my email address. Thank you so much for watching this video. Allah Hafiz.